Graphing data. So this is when we're going to be using visual representations to present different data from surveys, evaluations, or other databases to help make them easy to understand. Graphs and charts often condense large amounts of information into easy to read formats that are clear and effectively communicating points that are important to your study or evaluation. When you're selecting how to best present your data, you want to think about the purpose of your graph or chart and what you want to present. Then decide what variables you want to include and whether they should be frequencies, percentages, or categories reported. Some important things to remember about graphing. The graph must be self-explanatory, including a descriptive title, a labeled axes, so that X and Y axes of tables, and the units of observation. Some other characteristics of good graphics: clearly labeling and providing explanations, avoiding 3 dimensions. 3D pie charts kind of look nice, but they often distract the reader and get misinterpreted. You don't want to use more than one design in the same graphic. So sometimes you'll have like a pie chart with a pull-out piece to draw attention to that area. In general, for journal articles or professional write-ups, you don't want to do that. If you're presenting to a lay audience or your own organization, that may be something you want to highlight specifically, and then you could have that effect. But for the most part, you want to make them as simple and easy to read as possible and not mislead your reader. There's many different types of graphs, as you know, and it'll depend on what type of variable you have, how you're going to graph your variable. So first, there's a list of continuous variables. For those, you would want to use a histogram, a frequency polygon or cumulative frequency polygon, a stem and leaf display, or a box and whisker plot, which is also called a box plot. For categorical variables, you'll either use a bar chart or a pie chart. Histograms are used to display the data distribution for continuous variables. They show the frequency of observations that fall into different categories by fixed interval. The horizontal axis always represents the interval of interest or the variable of interest, while the vertical axis displays the frequency of the observations. Areas of the bars total sum up to 100% or a proportion of 1, so that each area of the bar represents a relative frequency. There are some different ways to produce these in SPSS. You can go to Graphs in the menu option, then click Legacy Dialogs, Histograms, or as I pointed out the first time we looked at SPSS, if we go to Analyze, Descriptive Statistics, Frequencies, then we click on that Charts button, there's a histogram option there. Oops. We have a number here in the bottom that shows that the number is 127, while the number up here is reporting 138. So there's some discrepancy between those, which probably just means that the sample size total was started to be 138, and the total non-missing data was 127 individuals. And then we have different heights of bars, so the occupational prestige scores varied from 20 up to, we'll say 75 approximately. Here's another histogram for BMI, and this one just shows how BMI kind of goes up quickly and then goes down rather slowly to the higher BMI displays. This data is from 3,480 participants of the Framingham Offspring 6th examination. And there's an article that this came from. So this is actually from that journal article. Now this is a write-up of what that histogram that we just looked at, the BMI histogram, what it's actually showing. So this is a direct quote from the article that was written so that you can see the professional language that's used to describe graphs. The histogram in figure 2 shows that the distribution of BMI for 3,480 participants at Framingham Offspring Examination 6 in intervals of width of 2.0 kilograms per meter squared, lower limit 15, upper limit 55. The distribution is neither bell-shaped nor symmetric, but is peaked and has a long right tail, positive skewness, and kurtosis. About half of the BMI values are between 24 and 31. Recall, Q1 equals 24.4 and Q3 equals 30.6 kilograms per meter squared. The median is 27.2 and the mean is 27, the mean is 27.9 kilograms per meter squared. Because of right skewness, mean is better than median. The mean is greater than the median. A small number of individuals have extreme values with BMI of over 50 kilograms per meter squared. So that's a description of that last figure 2 from the BMI in the Framingham study. So what this is basically telling us is that there was the lowest BMI value reported was 15, the highest value reported was 55, Q1, or the first quartile, the first fourth of the data had a value of 24.4, the third quartile had a value of 30.6, the median value was 27.2, and the mean was 27.9. Since the data was skewed to the right, the mean is higher than the median. And there are a small number of individuals who had values greater than 50, which is extremely obese in terms of the data here. Now we'll talk about frequency polygons. These use the same axis as a histogram, and they mark a point at the same height as the histogram's bar in the midpoint of the class interval. Then the points are connected with lines, and at the ends, the points are connected to the midpoints of the previous and succeeding intervals of zero frequency. I know, confusing, right? You can only use these with continuous data. This is constructed by marking a point at the same height of the histogram's bar at the midpoint of the interval. At the ends, the points are connected at zero frequency. Frequency polygons can be superior to histograms to provide comparing two frequency distributions. So here are some different shapes of frequency polygons. Sometimes they may be symmetrical, where the left side is very similar to the right side, and that median point. And that's kind of the classic bell-shaped distribution. The second option is bimodal, which means it has two peaks, and this type of distribution could represent overlapping groups of males and females. The C option looks like a rectangle, and this is called a rectangular distribution. And this means that it's just showing that each class interval is equally represented. Part D is showing skewness to the right. So there's a peak on the left and there's more data, but there's not necessarily more data, but it extends further out to the right than it does on the left. So it goes like climbing up a mountain fast and then slowly working your way down. That would be skewed to the right. Skewed to the left is slowly hiking up a hill. Then you get to that high point, and then you sprint down on the other side. So I hope that's a good way to explain it. Um, Another way to think of it is positive skewedness is because the taper is to the right direction, the right hand direction, and a negative skewness is tapered to the left hand direction. Hopefully that'll help you one of those descriptions. Here's the frequency polygon drawn onto the Larson histogram of BMI. So I know it was confusing where the 0 point is of the previous midpoint. That was kind of a hard explanation to conceptualize. But here, the lowest point was in the category of, it looks like 18. So the previous point is at 0 then. So we connect to that x-axis at 0 in the 16 class interval. And the same thing for 54 at the end. There's no individuals reported at 54, so that's where the class interval comes back down for the frequency polygon, connecting at the value of 54. These are most valuable to compare two different groups distributions. So this example compares different age groups and their serum cholesterol levels. So the ages of 25 to 34 have lower cholesterol levels than the ages of 55 to 64. And again, note here that the relative frequency is reported as the y-axis. The serum cholesterol level is reported as the x-axis, as well as those units, which is milligrams per 100 milliliters. And then we have a table number or a figure number. So this is figure 2.5. And we have a frequency polygon. It tells you the title then is Frequency Polygon Relative Frequencies of Serum Cholesterol Levels for 2,294 U.S. males from 1976 to 1980. Cumulative frequency polygons are also known as ogives, and this is where the horizontal axis is the same as for a histogram, but the vertical axis displays cumulative relative frequency or cumulative frequency. Although the horizontal scale is the same as that used for a histogram, we want to place a point at the upper class boundary of each class interval. Each point represents the cumulative relative frequency for the class, but we want to note that not until the upper class boundary has been reached have all the data of a class interval been accumulated. And then this is completed by connecting all the points, and then we can obtain percentiles or compare sets of data. Here's an example of what an ogive might look like, or a cumulative frequency polygon. This particular ogive is illustrating the data on systolic blood pressure in smokers versus non-smokers in the Honolulu Heart Study, which is actually one of the data sets we use in this class for homework. So here it looks like the x-axis is the systolic blood pressure measured in millimeters of mercury. The starting value is 89.5, and then our highest value is 209.5. Then our cumulative relative frequency, it doesn't look as normal as a normal y-axis. So the percentiles, or they are percentiles, they're kind of spaced out a little differently than you might normally see. So this doesn't list every tenth or 10%. We see 20%, then we skip to 40%, but then we have 50 and 60%, then we skip to 80, but then we have 90 and 100%. So it's a little different looking than the normal y-axis, where you have every interval is at least labeled. Here we don't have that. This is actually has been summarized in text, where you would want to say something like this. In figure 3.5, we can see that 90% of the non-smokers and 86% of the smokers had systolic blood pressures below 160 millimeters of mercury. The ogive gives for each interval the cumulative relative frequency. That is the percentage of cases having systolic blood pressures in that interval or a lower one. Percentiles can be obtained from this. So the 90th percentile is that observation that exceeds 90% of the set of observations and is exceeded only by 10% of them. Percentiles can be readily obtained. In our example here, the 50th percentile, or the median, for non-smokers is a blood pressure of approximately 127.5 millimeter of mercury, and the 90th percentile is 159.5 millimeters of mercury. And how you figure that is out, you go up the y-axis to the percentile, or the decimal place in this case, that you're looking at. So 50th percentile would be the 0.50. Then you want to go over until you hit that frequency plot with the non-smokers. And when you get there, you want to look down to see where that hits approximately on your x-axis with the blood pressure. And the same thing with the 90th percentile. So that's how you get them. So we don't use these a whole lot in class. I'm just exposing you so you understand what they look like if you do see them in the future. Another example of a cumulative relative frequency plot is for BMI by sex among participants in the Framingham Offspring 6 examination. So some questions here are, do men or women have a higher BMI at the 25th percentile? So we want to note that the male values are the light gray color drawing line, and the female values are the dark black looking line. So at the 25th percentile, that's where we want to go up that y-axis and find 0.25 approximately. And then we want to see whose value we run into first. And in this case, it looks like we run into the females first, which means that males have a higher BMI at the 25th percentile. Because where it intersects for females would be at about 21 or so, 22 maybe, and where it intersects for males is more like 25. So a BMI of 25 is higher than a BMI of 21, which means men have a higher BMI at the 25th percentile in this example. And then it also asks at the 95th percentile who has the higher BMI. So then we want to go up that y-axis to 0.95 and come over to see who we run into first. In this case, it looks like we have the descriptive text write-up for that graph we just looked at on the previous slide is as follows from this journal article that was published in 2006. The cumulative relative frequency plot in figure 3 shows BMI separately for men and women. Clearly, the BMI distribution is shifted to the right for men relative to women, such that most quartiles are higher in men than in women. For example, Q1 is 23.4 in women, but 25.5 in men, and Q3 is 30.2 in women, but 30.9 in men, except toward the upper end of ordered values. where the 90th percentiles are 34.7 in women compared to 34.1 in men. Now we'll talk a little bit about stem and leaf displays. This is used to display frequency distributions for continuous variables. Each stem represents the class intervals, and leaves represent the string of values within that class interval. You can create these in SPSS using the Analyze Descriptive Statistics Explore function. That's just how you get to it. I'm not going to actually expect you to use that for this class, but if you needed to know how to get there, that's how you would find it. So here is an example of a stem and leaf display showing systolic blood pressure of 63 non-smokers. So on the left are the list of stems or intervals. In the middle is the leaves, which are the observations. And then on the very far right is the frequency or total number of leaves in that interval. So we want to arrange the last digit of the observations for the stems from lowest to highest, and that's what we call the leaf. The leaves portray a histogram laid on its side or flipped 90 degrees, so it's easy to note the size and frequencies in the different intervals or stems. This way we're displaying all the observation and providing a visual description of the shape of the distribution, and usually we present a stem and leaf display together with a conventional frequency distribution. From this particular stem and leaf display, we can see that the systolic blood pressure data, the range of measurements is from 92 to 172. The measurements in the 120s occur most frequently, with a measurement of 128 being the most frequent in the whole stem and leaf plot. We can also see which measurements are not represented. In this case, the stem of 180 to 189 is missing, which means there are 0 frequencies that are shown in that, or occurred in our sample of 63 non-smokers. Another example of what SPSS puts out for you if you ask it to make a stem and leaf display is this table here. So on the left in this table is the frequency or the number of observations or the number of leaves that appear in each stem. And here we have the stem width being 10, and each leaf identifies one case. So here we have stem 2 with the values of 1 through 4. So this would be anyone who had an occupational prestige score of 21 through 24. Then the next row identifies anyone who would have an occupational prestige score of 25 through 29. So it's split up into groupings of 5. So it's actually would be anyone who scored at 20 to 24, but we don't have anyone in this example that scored at a 20. And then the last row at the very bottom is a score of anything from 70 to 74. So we didn't have anyone score higher than 74 in this sample. And this is just showing you the breakdown. And the frequency, the highest number of individuals reported scores between 40 and 44. With a total of 18 of them reporting scores in that range. And then the most reported score, I would say here, would be a 42, 47, and 51. Actually, I think 51 is probably more reported than those other two. So 51 would be the mode in this case. Box and whisker plots, or box plots, are used to display frequency distributions for continuous variables. They display a summary of data, not every observation, like the stem and leaf display. It's one axis that displays the values and observations, so it's useful for showing symmetry and dispersion of data. The box in a box plot represents the middle 50% of the data. So the box ends represent the 25th and 75th percentiles, or the Q1 and Q3 markers. And then the horizontal line through the middle of the box then would represent that median or 50th percentile. The whiskers at the end extend to the most extreme observations in the data that are not more than 1.5 times the height of the box. Points outside of those whiskers then are outliers and are identified usually by symbols or asterisks depending upon what program was used to make the diagram. In SPSS, you can make a box plot by going to Graphs in that menu and then clicking Legacy Dialog and then Box Plot. This is an example of a simple box plot which illustrates the frequency of systolic blood pressure values among 100 men in the Honolulu Heart Study. So it's a one variable box plot. This one is listing the systolic blood pressure on the y-axis. So from 80 to 220 was our range of values. It looks like our median value was about 130 here, with our Q1 value being 118 and our Q3 value being 140. Then our whiskers extend out down to about 90 and up to 175. And then we have a few outliers that are listed there's about 4 of those in this data of 100 men in this study. Now this box plot shows left ventricular mass based on BMI category in women. So it's the frequency of one variable, ventricular mass, by another variable, that other variable being BMI group. So you can compare then the mass, the left ventricular mass, by different categories of weight or BMI. So this is the Framingham study again. We had 9 individuals who were considered underweight, 712 that were normal weight, 645 overweight, and 477 obese. So you can see that in our underweight category, our box is narrow, the whiskers are narrow. That's because there were only 9 individuals who fell into this category, so it makes it very narrow. And their values were close together. The normal group has a bit bigger of a box, similar in size, I would say, to the overweight and obese groups. So that means their Q1 and Q3 scores are similar, but the median values have gone up significantly from the underweight category. So the underweight's median value was just under 100. The normal weight is about 130, 140. The overweight is 150, and the obese is probably closer to about 165. Then we have a number of outliers in the normal, overweight, and obese. We actually have outliers in the overweight that have a higher left ventricular mass than some of those individuals in the obese category. But they're all higher than the median value. There's none that are below that first quartile and that whisker. That's 1.5 times the width of the box. So that's just one way you can compare and see how those values differ among different groups of individuals. A descriptive text of that box plot comparing the 4 categories of BMI is shown here. This is taken from the article itself. So the box plot in figure 4 shows descriptive statistics for left ventricular mass according to BMI categories for women in the Framingham Offspring Study at examination 6. Note that there is a clear progression from lower to higher left ventricular mass associated with increasing BMI category, both in median and means. In addition, the spread of the data values increases across the BMI categories, modestly for the interquartile range, but markedly for the whiskers and extreme values. So the interquartile range is that Q3 minus Q1. So that was me talking about how the box sizes look a little bit similar. But it was also saying that the spread of the data increases in the whiskers and those extreme values from normal to obese to overweight to obese. The next one we're going to talk about is bar charts. Bar charts are used to display categorical data. The horizontal axis represents the categories for your observations, and the vertical axis displays the frequency or relative frequency of observations within the category. If it starts at 0, that's what you want. If you can't start the axis at 0, if that would take up too much room in a journal article or something, you want to make sure you use broken bars to show your audience that there is a lot more information that is missing. But ideally, you want to have got that start point at 0. Bar charts should have bars that are separated, so you're not implying that one category flows into the next, not like a histogram where the bars are right next to each other. And the heights of the bars represent frequencies or percentages. In SPSS, you can get to a bar chart by going to Graphs, Legacy, Dialog, Bar. I think you can also get there using the Analyze, Descriptive Statistics, Frequencies, and then checking off a bar chart. Sometimes you'll want to arrange your categories alphabetically or by frequency within the category or on some other rational basis. So the way you organize the categories on that x-axis could be any of those ways. We often arrange them for frequency with the least frequent and ending with the most frequent. And to we want to show that in a bar chart, relative frequencies are shown by height, but in histograms, relative frequencies are shown by the area within the bars. So just remember that if we have a bar chart, frequencies are shown by height, whereas a histogram, relative frequencies are shown by area. We have an example of a bar chart presenting a percentage of respondents residing in various U.S. regions. On the bottom, we have 3 regions of the U.S. listed. We have the Northeast, Southeast, and West. It's not super descriptive in my opinion, but it's what we've got. And then in the percentage, we have 0 at the very bottom on the y-axis going up to 50%. So none of these 3 options contain 50% or more of our data. They're all under 50%. That Northeast region looks about 45% of respondents in this survey. The Southeast is about just over 30%, and the West is probably 25% or so. Finally, a little bit about pie charts. They're used to display nominal or ordinal data. So that is arranged into categories. It's a circle that's divided into wedges corresponding to percentage frequencies of a distribution. These are also useful in conveying data that have a small number of categories. It's kind of hard to draw pie charts by hand just because the area is proportional to the frequency. So this can be done in SPSS, or I'm sure this has been done in Excel as well. In this example on this page, we have a figure showing administrators' attitudes towards placing nutrition in medical school curriculums. So this was a Likert scale option of strongly agree, agree, neutral, disagree, or strongly disagree. In this example, 38% of the respondents disagreed, 22% strongly disagreed, 10% were neutral, 12% agreed, and 18% strongly agreed. So for a pie chart, the total has to equate to 100%. Otherwise, it wouldn't be a circle. So it's just something to remember. These are a number of charts that you'll see. If you're interested in learning how to use the SPSS stuff, let me know, and maybe we can do a little bit of that. If not, we'll probably just keep it pretty basic with the histograms.